Ses kontrol.
Günaydın. Alo. Seste bir sıkıntı yok, tamam.
Good morning, distinguished guests, esteemed professors, researchers, colleagues, and dear participants. On behalf of Istanbul's Atlas University and the organizing committee, it is my great pleasure to welcome you all to the 6th World Energy Storage Conference 2026. My name is Associate Professor Şaber Ömeraki Çekirdekçi, and it's my pleasure to be your moderator for this opening session. We are delighted to welcome distinguished scientists, researchers, academics, industry representatives, and participants from Turkey and different parts of the world. West 2026, organized in collaboration with Istanbul Atlas University and Ontario Tech University, provides an important international platform for exchanging scientific knowledge, presenting recent developments in energy storage, and establishing new collaborations for a sustainable energy future. To officially begin our opening session, I would like now to invite you to watch the WESC 2026 conference promotional video. Please enjoy the video.
Better use of renewable energy. Solar and wind power are central to this. Our world is facing increasingly serious environmental, economic, and social challenges caused by climate change. Rising temperatures, droughts, floods, wildfires, and the depletion of natural resources show that we must transform our energy systems. A greener and more livable future requires lower carbon emissions, reduced dependence on fossil fuels, and wider use of renewable energy. Solar and wind power are central to this transition. However, the sun does not always shine and the wind does not always blow, while energy demand continues every hour of every day. Energy storage provides the essential link between renewable generation and continuous demand. It captures surplus clean energy, prevents waste, and delivers electricity when it's most needed. For this reason, energy storage is not simply a technical option. It's a strategic necessity for climate action, environmental protection, carbon neutrality, and energy security. Storage systems help balance electricity grids, control frequency and voltage, manage peak demand, reduce interruptions, and limit the need for fossil fuel backup plans. They also support the safe integration of electric vehicles, heat pumps, data centers, and smart cities. Different needs require different solutions. Batteries and flywheels provide rapid, short duration support, while thermal storage, pump storage, hydropower, compressed air, and hydrogen can supply longer duration or seasonal flexibility. The energy system of the future will therefore rely on integrated and hybrid technologies. Efficiency, cost, safety, durability, recycling, and environmental impact must be considered together. Source Conference 2026 brings science, technology, industry, and international cooperation together to create safer, cleaner, and more resilient energy systems. Because storing energy is not only about saving electricity, it's about protecting clean energy, our environment, energy security, and the future of generations to come.
It is now my pleasure to invite our conference chair, Professor Dr. Zafer Utlu, to deliver his opening speech. Professor Utlu, the floor is yours.
Dear distinguished guests, estimated professors, researchers, colleagues, and participants, it's a great pleasure and honor to welcome you to the 6th World Energy Storage Conference here at Istanbul Atlas University. We are especially pleased to organize this important international conference in collaboration with Ontario Technical University, bringing together distinguished researchers, academics, industry representatives, and experts from different countries to exchange knowledge and discuss the future of energy storage technologies. Today, we come together at a time when the global energy systems is undergoing one of the most significant transformation in its history. Climate change, increasing energy demand, energy security concerns, and the urgent need to reduce greenhouse gas emissions are reshaping the way we produce, distribute, store, and consume energy. Renewable energy sources such as solar and wind are playing an increasingly important role in this transformation. However, renewable energy also presents an important challenge. The sun does not always shine, and the wind does not always blow, while our demand for energy continues every hour of every day. This is precisely why energy storage has become one of the key technologies of our sustainable energy future. Energy storage is no longer simply a supporting component of energy system. It has become a strategic necessity. From batteries and thermal energy storage to hydrogen, pumped hydrogen storage, and emerging innovation technologies, energy storage provides the flexibility required to integrate renewable energy sources, stabilize power systems, improve energy and exergy efficiency, and strengthen energy security. At the same time, storage technologies will play a critical role in the decarbonization of transportation, buildings, industrial process, and cities. However, achieving a sustainable energy future requires more than technological development alone. We need multidisciplinary scientific research, innovation engineering solution, effective policy, economic feasibility, international cooperation, and importantly, the exchange of knowledge and experience. This is where international scientific events such as the World Energy Sources Conference become particularly important. Over the coming days, this conference will provide an important platform for researchers, scientific, academic, engineering, industry representatives, policymakers, and young scientists to share their latest studies, discuss emerging technologies, develop new perspectives, and establish new collaboration in the field of energy storage. I strongly believe that some of the most valuable outcomes of this conference will come not only from presentation themselves, but also from the discussion, question, exchange of ideas, and new collaboration that begin here. Scientific process becomes much stronger when knowledge is shared and when researchers from different disciplines and countries work together toward common goals. Before conclusion, I would like to express my sincere gratitude to everyone who has contributed to making World Energy Sources Conference possible. First of all, I would like to extend my special thanks to Dr. Yusuf El-Görmüş, Chairman of the Board of Trustees of Istanbul Atlas University, for his valuable support and his contribution to this international scientific event. I would also like to express my sincere appreciation to Professor Dr. Ersoy Kocabıçak, Rector of Istanbul Atlas University, for his continuous support of scientific research, international collaboration, and the organization of this event. I would also like to thank Ibrahim Dinçer for his valuable collaboration and contribution to the organization of this conference. My sincere thanks also go to all members of the organizing committee and scientific committee for their dedication, hard work, and tremendous efforts in preparing this conference. I would also like to thank our distinguished keynotes and invited speakers, session chairs, researchers, and all participants who have traveled from different countries to share their knowledge and experience with us. Your presence and scientific contribution are what make this conference truly meaningful. Finally, I hope that the Sixth World Energy Storage Conference will not only contribute to advancement of energy storage science and technology, but will also inspire new ideas, new partnerships, and new solutions for a cleaner, more secure, and more sustainable energy future. Once again, welcome to World Energy Source Conference, welcome to Istanbul Atlas University, and welcome to Istanbul. I wish you all productive, inspiring, and successful conference. Thank you.
Thank you very much, Professor Utlu, for your inspiring remarks and for your valuable leadership and contribution to WESC 2026. Esteemed guests, our rector, Professor Dr. Esor Kocabıçak, is unable to address us personally today. However, he has sent a special message to all participants of WESC 2026, and it's my pleasure to share it with you. Distinguished scientists, esteemed guests, and dear participants, on behalf of Istanbul Atlas University, it is my great pleasure to welcome you to the 6th World Energy Storage Conference, WESC 2026. We are very pleased to host this important international conference and to bring together distinguished scientists and experts from different countries. I would like to thank Ontario Tech University, the conference chair, the organizing and scientific committees, our distinguished speakers, and all participants for their valuable contributions. I wish you all a productive and successful conference. Welcome to Istanbul Atlas University and welcome to WESC 2026. Thank you very much to our rector, Professor Dr. Esor Kocabıçak, for his kind message. Dear colleagues, we will now proceed with the keynote talks. Our morning keynote session will be chaired by Professor Dr. Seda Keskin Avcı. Professor Avcı, thank you very much for chairing this important session. May I have you to the stage, please? It is now my pleasure to introduce our first distinguished keynote speaker, Professor Dr. Hussam Juhara. Professor Hussam Juhara is Professor of Thermal Engineering and Vice Dean for Research at Brunel University, London. His research focuses particularly on heat pipes, heat exchangers, thermal management, industrial waste heat recovery, and sustainable energy technologies. He has extensive experience in international research projects and the industrial application of advanced thermal technologies. Today, Professor Juhara will deliver his keynote presentation entitled Advances in the Utilization of the Heat Pipe Technology in Industrial and Renewable Energy Applications. Professor Juhara, it is a great pleasure to have you with us at WESC 2026, and the floor is yours. Thank you.
It doesn't work because it's. Thank you. Good morning. Good morning, and what a pleasure to be back here. I came here for the first time to Turkey actually in December 2024, invited by my good friend Professor Ibrahim Dansha and Professor Zafi Utlu, and what a lovely place you have. I came since another time, and now this is my third, and all with the same group. So it's a pleasure to be here. My presentation today will be actually following on from the previous one that I did here. At that time, I did mention one project and other two coming. That project is now completed. I will show you some results, and the other two are halfway through. But what I'll try to do also is, I'm sure we have young researchers here, early career academics, and also senior colleagues. I will share what we have been doing over the last couple of years since I was here, and how our knowledge and experience in academia and research actually makes a difference. So I will start by basically introducing the technology that I have been working on for the last 21 years now. The heat pipe technology, as you may all know, it's basically because of it, we do have these laptops that we have in our hands at the moment so thin. And even the new iPhone, I heard, has a heat pipe in it. What they do, they actually transfer the heat with a superconductivity capability. And by doing so, we call them thermal superconductors. So they transfer the heat at conductivity of thousands of times that of the metal they're made out of, meaning you don't need to run fluid through them to transfer the heat. So just to give you a brief introduction of the science behind it, heat pipes, they usually are hermetically sealed tubes. They can be other shapes, but the inner structure is hermetically sealed. They have a saturated environment with small amount of working fluid, and this fluid is saturated. That's the key. The moment you expose the part that is filled with the fluid to heat and the other part to colder environment, heat will be transferred by boiling condensation cycle. There are two types that are known. There are many actually when it comes to the way the heat transfer fluid is actually circulating. I work primarily with gravity-assisted heat pipes, meaning I don't have wicks in my heat pipes, and that allows me to have the flexibility of the size. So if we take a wickless heat pipe structure, you can see it in front of you. It's a tube, small amount of working fluid designed to cater for heat transfer rate of certain value for certain environments. The combination between the working fluid and the shell is subject to the environment and the working temperatures. Going deeper in the science, if you look at that tube, in order to design it, you have to actually do every single heat transfer calculation that you know of. So you have to do convection, conduction, radiation, boiling heat transfer, condensation heat transfer, two-phase flow, all of that to be able to design the system so it can function. So you end up with the thermal resistances being compiled, looking at ohm analogy, which is key for us. Once that is done, you build it, and then it can be done for various temperature regions. This is my hand holding the three heat pipes here. The first one is my hand holding a acetone heat pipe in a kettle. You can see where my hand is. The temperature is slightly lower because that's where the heat is leaving the heat pipe entering my hand. Between the kettle and my hand, it's an isotherm because basically there is no heat interaction with the environment except steady loss by convection, natural convection to the air. So you can see it's uniform temperature. And that's a beautiful thing about this technology, the uniformity of the temperature range in the environment. If you want to go for high temperature heat pipes, like for example, liquid metals, so we use sodium, for example, you can see me holding a sodium heat pipe, is for nuclear applications. Very complicated, still low TRL, lots of challenges, but I'm hoping one day they will be viable. But this is still low TRL level when it comes to using liquid metals. But still, lots of work on them. You can see me also holding the torch there, basically red hot metal, lots of challenges, but still just showing the way forward when the application comes. Digging further, if we take one of those heat pipes, which is a heat exchanger and it's all right, put many together in a box, separate the box with a separation plate, allow a hot fluid to go through the lower chamber a colder fluid to run in the upper chamber. These heat pipes will act as sinks. They will just absorb the heat from the bottom, shift the heat to the top, allowing this heat to be transferred to the fluid passively. In a conventional system, you can only do that by having a flow running through. Because these are heat pipes, this is done passively. So the only movement you have is moving the stream, the hot and the cold streams in the two chambers to allow the heat movement. There are so many advantages of such technology. I mean, nowadays, the biggest one is the multiple redundancy, but the most important is actually the passive operation. You don't need to run fluid through them to allow the heat to transfer from A to B. It is done passively. By doing so, you reduce the amount of mass, materials, reduce substantially the maintenance request or costs, and that is big, especially with the oil and gas industry. And I will show you a few examples that are making use of that. So many people say, well, it means I can use heat pipes everywhere. Well, I wouldn't. There are scenarios where really you don't need them. If you have a clean scenario like liquid to liquid, no challenges, clean gas to clean gas, again, no challenges. You know, you only use these technologies where you have challenges. And I can tell you, every time you see one of those chimneys, and I've seen a few yesterday, I'm hoping next trip I won't see them, because it will have more efficient system actually to recover this heat, because this is wasted heat departing the factory, joining the environment. These white blooms you see over there, they're mainly water condensing, but with that water, you also have sulfuric acid, nitric acid, other contaminants. These are joining the air that we breathe. Because they are lower than a certain level, they're allowed. But soon enough, this limit will drop down. So we have, as scientists and engineers, we have to do something to address that. So we use this technology now to address them, because basically we can keep the wall temperature inside the heat exchanger. In the hot region, for example, uniform, meaning I don't have cold spots. When you have cold spots, you end up with acid condensation. We don't have that here. The same thing goes in the colder section. So that's having a uniform temperature in the hot region and the cold region is a huge advantage. We can control the temperature to stay always above the dew points of the acids. We don't have localized cold spots. If you study shell and tubes or cross heat exchangers, when you have accelerated flow, the heat transfer coefficient there will be much higher, leading to lower temperature of the wall between the two streams. When you have lower temperature, if this temperature falls below the dew point of the acid will condense there. And then slowly corrosion will happen. At one point, when it penetrates the wall, cross-contamination between the two streams occurs. If you're dealing with industries like the chemical industry or other sensitive industries, when you have cross-contamination, you have a very expensive repair and decontamination process. So this is something we actually have and eliminate. They're easy to clean, lots of advantages. The most significant of which, and that's where we take our academic hat on, we put the industrial hat off, we put the industrial hat on. Industries, they need to be able to get their money back in 2 years maximum. If the return on investment figure is larger than 2 years, you will have to put the fight. If it is larger than 3 years, you have no chance. They'll just say it's too expensive for us. But if they invest, say, €1 million, £1 million, and they get this £1 million back in 2 years, they will go for it. Most likely, they will say, yeah, that's a good investment, actually. Let's go for it. Anything above that is a challenge. So the economics is always important. And we as academics, sometimes we forget that. Yes, of course, it's important to keep the research going, but keep in mind, whatever we work on one day has to make sense, economical sense. Right, so let's now take the academic hat off. Let's put the industrial hat on. How do we link academia and research we do in academia with the industry? The answer is by collaborative research. So I am also the technical director of a company that manufactures my systems since 2007, and that gives me flexibility. So when I work with other collaborators, I always have in mind whatever I design will be manufactured. And that is key. That makes life easier. I don't have to go and look for people to manufacture. So Just to give you an example, this is a system that we installed in the UK. Before we install, we have to install virtually. The reason for that is to make sure we preempt any issues. Even the smallest screw, we know what it is and we know we have it. So we can actually go inside the systems. We can see what fittings we have, the DIN for the flanges, etc. We have to find all that out in 3D, working with all the partners before we even go to the site. And that's how we make sure we are ready. So we follow the waste heat recovery case building process by identifying the streams. So when a company comes and say, look, I have these fumes coming out, can you design a heat exchanger? It sounds simple, it's not. You have to look at the fumes, the composition, the temperatures. If I am to recover the heat, what do I do with the heat? And that's where this conference is very important. On many occasions, the heat, you can't use the heat straight away. You have to have energy storage. That's why energy storage and the recovery, they go hand in hand. You can't have one without the other. Energy storage can be in various forms, can be sensible, latent. It can also be in metals. It can be also in geothermal storage. There are so many ideas about storage nowadays that have been explored. I'm sure my other colleagues will cover them later. Once we understand what the streams and their composition, then we identify the technical specifications that are required. Because I'm working with heat pipe system, because these scenarios, they require heat pipe scenarios or systems, I look at the system, design it theoretically, run the mechanical design by the company that will manufacture it. If there are any issues, if all is good, we then go to the piping and instrumentation diagram with the site, make sure all the sensors, the control strategy, everything is in place. After that, we work on the implementation and the commissioning. So it's a long process, but at the end of it, if you do it right, everything goes without a hitch. Right? Can we see examples? Let's have a look. A typical heat pipe heat exchanger is a box or a cylinder, subject to the conditions inside. You can imagine it as a box. If you do a cut, it's a box separated by a separation plate. This separation plate separates the hot region from the cold region. So in this scenario, I have exhaust flow going in. The heat pipes are absorbing the heat from this exhaust, delivering the heat to the heat sink fluid. It can be air, it can be water, it can be anything. How do they look like? You can see here, they look like smooth finned if you want extended area, sometimes by metals. Nowadays, with the cost of materials, supply chain becoming really a challenge, we are opting to scenarios where if we have a system to be installed in Turkey, let's say, we design the system, we build the heat pipes, we send the heat pipes here, we build the carcass here in Turkey, so we cut the cost of shipping metals. So the only thing we ship here is the heat pipes because that's the core of it, and then we install everything when we commission. So lots of things happening. This box was actually went to India to be installed in a ceramic company. Everything was ready. The heat pipes arrived under supervision. They were installed. The system was commissioned in less than a week. We made heat pipes up to 20 meters in length. There's no limit regarding the dimensions. The only thing you have to do is design it properly, so it functions without hitting any of its limitations. So what about the systems that are in the market at the moment that came from this process? Here's a scenario in Canada. You can see simply a box here. If you take the box out, you can see a heat pipe system. Many heat pipes staggered in certain configuration based on the thermal design with a separation plate in the middle. You can see the exhaust flowing at the bottom. Heat is absorbed and provided to the combustion air that takes that heat and heat the combustion air. By doing so, you don't need as much fuel as you would if the combustion air was cold. So this is a very good example of a system that until now is operational. We can go big, and with waste heat recovery scenarios, the bigger you go, the better the economics. So this system here in a steel company in the Czech Republic is 12.6 megawatts, payback time 6 months. It recovers heat from exhaust coming in at 286 degrees, coming out at 156 to heat coke gas up to 197 degrees. Typical application in waste heat recovery systems, and it's really running like a clockwork. The only thing we have to do with this system is every 5 years, we change part of the tubes to make sure that they continue operating without any issues. Going back again to Canada, shale gas was a big topic in Canada for a while. I don't know, Ibrahim, if you remember those days. If you want to extract shale gas, you need to have two things: electricity and hot water. So they used to have electricity from gensets like this one here, but the hot water, they used to burn diesel. So what we did, we installed a heat pipe heat exchanger at the cylinder at the end after the genset. The genset providing electricity, the heat pipe heat exchanger providing hot water. The site is operational. Payback 3 months, was really good. And then when they finish working on the site, they collapse the stack and they go to another site. So it was really nice mobile unit that just perfect. 3 month payback was really good. A big thing now in China in particular, they don't like ejecting steam. Steam is valuable, it's water, lots of energy. So steam condensers at the moment are a really big topic. We have lots of these scattered around Europe and the UK. It's simple really in thermal design. You condense the steam at the bottom, the heat is then absorbed and sent to the top. In this scenario, we're heating water in a dairy company in Northern Ireland. You can see it's very high energy system, 446 kilowatts, large capacity condensing steam that is otherwise was ejected at 105 degrees. We cool it down to 95, we recover the water, and we heat in the process water from 10 degrees to 88 degrees for pasteurization purposes. Sometimes, even though you think, okay, well, we have a TRL9 unit, you end up still with challenges. So this company called Buffetti in Italy, they incinerate clinical waste. And they tried everything in every heat exchanger to work there. These heat exchangers will just get clogged. Lots of particles, and they clog the system. So I had to use CFD. I don't know if we have any researchers here who use CFD. Anyone uses CFD? Here you are. I had to do it myself. And that wasn't easy back in 2013. It's not like nowadays you have ultra-fast computers, etc. I had to use CFD here for this design to ensure that during the process, the particles that flow through don't stay in. So ensure that they continue suspended and they pass the heat exchanger without settling in it. And then they go to a back filter that operates at lower temperature. So the fumes were coming at 610 degrees, being cooled to 150. In the process, they heat water to 90 degrees. And that water was sent to the local area as district heating water. So before that, the people were complaining about the smell and lots of things. After we installed the system, people were getting their hot water at 30% the price. So they were happy. They weren't complaining anymore. And because of the use of the CFD, it was more expensive. Hence, the payback here was around 18 months. Typically, those units will have about 1.5 years. But that's another example. We applied the same thing in the ceramic industry in the UAE, in rack ceramics. You can see an example here. And, various designs, like, for example, the modular shape you see at the top, it was done in collaboration with Sparax-Sarco steam generator. And you have two other modules. One module preheating water for the steam generation, and the other one heating oil for various applications in the factory. And you can see it installed here. So going modular is nowadays quite big. However, the biggest industry that we really wanted to work with was the oil and gas. Because they have, nowadays we say oil and gas, lots of emissions, problems. I hope you will understand when I say oil and gas is not bad. We need it. We need it in everything we do. When I came here this morning, the car was using fuel. There's no way we can just stop using it. So I would say oil and gas is not bad. It's a saying of an old friend of mine. Actually, emissions are. So if we can eliminate the emissions somehow, then we can use the energy without the bad impact. But to get to the oil and gas as a heat exchanger manufacturer, it's not easy. We have to be indexed in the American Petroleum Institute handbook, and that was a long process. But I'm glad to say that process basically was completed a few years back. And if you look at clause F2.3.1.3, heat pipes, air preheaters are now there. That's it, really. Once that was there, we started the work. Started the work in collaboration with, starting with China. In China, they have lots of oil being extracted from the seabed. And the issue with that oil is quite viscous, difficult to pump. So what they do, they send steam to mix with the oil, and then they are able to pump it up. They used to use shale gas and other things to burn and create the steam, which was quite expensive. What we did here, we installed a heat pipe steam generator on an oil rig. You can see it actually sitting surrounded by the sea, generating steam at 180 degrees. This steam is then injected to the seabed and basically making the pumping much, much easier. 6.4 megawatt unit, payback 7 months, validated. That was the first venture, and the oil and gas proved ourselves that we can do it. Then, after many years of collaboration with ExxonMobil in the US, who were very supportive of our process to get in the API index, we started actively working with them. So we installed many units in Baton Rouge and in Joliet, air preheaters mainly. The key there is retrofit. They have lots of old heat exchangers that are not doing anything. So the idea is to take the old system out. You can see the process there. Take the old system out, put the new system in, which is a heat pipe system, and then press the button, everything back to normal. In fact, we managed to get the system really efficient to the point now we have many units installed, and we are manufacturing too as we speak. So the strategic collaboration with ExxonMobil is really going ahead nicely. They go big. The sizes there and the oil and gas are really big. So this is 7.1 unit, which is a small one. We have 30 megawatt unit actually was installed, and we have others now being negotiated. In addition, we are in direct communication with BP to explore the option of using the heat pipes there. But you can see it's difficult to get into that area, but once you're there, and that's the key. So these are examples of industrial ready units. But do we have everything now? Of course not. So in my group, I am funded by everyone here, and we design systems that are basically, you might be, if you look at this photo, I don't know if you've seen it before, this is my pride and joy. It's my solar roof. It's a heat pipe solar roof. So these panels, each panel is a single heat pipe. And if you put a PV on top and you keep that panel at lower temperature, the PV will give you 15% at least higher electricity output. The heat that you absorb, you can push that heat to a heat pump, elevate the heat, store it until you need it. So it's beautiful. We have many of these systems now scattered. Lots of students actually finished their PhDs on them, which is fantastic. And the plan is now to install it across Europe on various locations. Now, if you don't need the hot water, that's a challenge. But in northern countries and the UK, hot water is a requirement. So we can actually use them there. And the plan is to put them on roofs, replace the old tile system with them in new buildings. That's something we are also working on. And it's really going fantastically well with regards to what else can we do. So we're now looking at facade of the buildings to put them there, lots of activities. And I hope the next conference, maybe I can show you some photos of that. Lots of activities are going. However, we can still see these. And that's really annoying when you see it. I mean, if you are really passionate about the environment, which I'm sure all of us are, this is actually something that we are inhaling. Our children are inhaling. And that's something we need to work and do something about. So having these, something that we should get rid of in the next 5 to 10 years. So I did mention this project when I was here 2 years ago. We started the iWay project. The idea was recovering the heat and condensing what's in those fumes. So condensing the acids and the water. In the process, recover the heat and also recycle the water. Very challenging. Many people actually said you can't do it. And they were right at the time because the challenges were really big. I'm pleased to say we actually managed it. So this is the thermal design. From thermal point of view, the idea is because these heat pipes, each one is an individual heat exchanger, I designed them so I can tell each heat pipe for each one what is the wall temperature, so I can control what am I condensing and where. And by doing so, I can use cost-effective materials. So stage one of the heat exchanger, I'm just cooling without any condensation, so I don't need premium metals. Stage two, I condense the first acid, which is usually sulfuric acid, H2SO4. So for that, I use metals that can withstand the corrosion. From that acid, stage three is where basically nitric acid more commonly condenses, has lower dew points. The goal is to get to stage four, which is where I get the large amount of latent heat and condensing water. Recovering the water, which is the main flow, it will be contaminated with the acids. This water is then treated, recycled, reused in the factory. We have partners also looking at removing the sulfuric acid, which has value, and other acids that's separating them and also have their economical value unlocked. For that, we had to build a large lab. We tested various metals. And we looked at each metal to see which one to use. Of course, the idea later to go for coating, but we had to do the test before. We found the metals that we need to do. I'm going to show you two demos. We had three, actually. The last one was just radiative. It's not relevant to this. The first demo was in a chemical producing company called Aliflo. They produce aluminum fluoride. You can see we had to build the setup in 3D, as I mentioned before, to the smallest bolt. So we can actually tell, if you zoom in, you can even tell what size is the tube, what screw are you using. Moving from that to manufacturing the unit, this is the unit being manufactured. Preparing the site, installing the unit, you can see the installation on the site, preparing the platform, having the unit installed. So this unit was installed and tested November 2025, and it was the most difficult unit maybe we worked on. Lots of challenges, including hydrofluoric acid, which is not really easy to handle. The second unit is a unit in a ceramic company, Atlas Concord, that have been with us for many years in projects. But this time they want to go big. They want to go really big. The idea is to cool the exhaust, condense the water, and reuse the water and the heat. We're talking here about a very large system, 1.3 megawatts. When you say 1.3 megawatt for an R&D project, it is big. It's really big. I'm pleased to say the system is now installed. I'll just give you an idea of the size and how it operates. So I have a video for you here. You can see in the video the setup. Exhaust goes in. This is the heat exchanger. It's about 4 meters in height. Prepared to preheat air. The air is then goes to the spray dryer. The exhaust comes out here. And if you look at the bottom, which we're going to see now, you see water condensing and flowing down. That water was just going with the fumes to the atmosphere. It is now captured here. Now, to see the water clearly, I have the other video for you. So if you look here, we had in this test 600 liters of water an hour condensing, treated, recycled, and reused back in the factory. We talk about Italy. Water has value there. And because, you know the issue with water in certain areas. It's not only water, it's energy. So we are recovering now the water and the energy. And these white fumes coming out, they stopped here. Now, there is still a bit of work to do, and you have to use special pumps, etc. Now, iWays was a fantastic thing for us. We demonstrated that we can actually do the condensation. I'm not going to cover it here. I don't think the time allows me. But since iWays was completed, we started 5 new projects, large ones. One of them is of interest to this conference. It's called the StreamStep project. I believe Professor Otlo was in Rome last week. We showed basically the value. We are now condensing. Many companies, they have low-grade heat, but they say, well, if we recover it, what do we do with the heat? having water at 40 degrees or 50 degrees is not really useful to us. That's where energy storage and heat upgrades come in. So the follow-on project from iWays is called Stream Step, where we take the low-grade energy, we elevate the temperature to 150 and 200 in two areas using high-temperature heat pumps. Good. Then what? We still have CO2 in the fuels. Even when we condense, you still have this CO2 that was generated. So we have other projects. One of them called enhancement. It's halfway through. The idea is use the condenser economizer, use a heat pump, and carbon capture and storage. So you can see the way things are. Lots of things happening. Our hope in the next 5 to 10 years, what you will end up going up is simply air that you can inhale without any issues. Lots of work, lots of money being spent to get there, but hopefully soon I will be able to update those books and include these case studies. But if you are interested in what you saw, there are so many in the books have been already covered. And with that, I thank you, Professor Otlo, for your kind invitation to Istanbul again. And it's a pleasure to be here today. Thank you.
Thank you very much, Professor Juhara, for your highly informative and inspiring presentation. We sincerely appreciate all your contributions for the conference. And as a token of appreciation, we would like to present a plaque of appreciation to Professor Hussam Juhara. May I kindly...
Any questions first?
Yes, shall we have the questions first? Sure.
Thank
Sorry.
you very much. Thank you. Thank you. No, please do. I really can't. Not now. It's not my place. But I'm sure next time maybe partners can come here and talk about it. I mean, the question about carbon capture, the technology we are using are cutting-edge technologies, and we are pushing to protect it. And as you all know, it's still low TRL, so lots of activities happening.
Sure, sure. Questions? There is one from.
I'd like to ask about the use specific working group in this part, because there again, the transport contamination is very critical. So the type of fluid is going to be very critical. So anything, because we know refrigerants are commonly used, but anything beyond you recommend in terms of research or, for the sake of innovation, and also probably some new directions, to young researchers around here.
That's a very important question. Thank you. I will just repeat it just in case. So the question is, what sort of advice I would give to early career researchers on research to do with generating new fluids as a topic of edge topic, for example? And that's an amazing question. So in most of my units that are commercial, we use water is good from 50 degrees to 300 degrees inside the heat. So that range is good for water. Water is perfect, environmentally friendly, and nothing wrong with it. So in scenarios where you have exhaust coming in at 1,200 degrees, you can still use water as long as you can cool the heat by quickly enough to kill the temperature inside at below 300. When you go beyond that, when you can't do that, and the temperature inside the heat pipe goes above 300, you have other water. So we have a fluid called diaphragm A, which is good up to 395 degrees. But it is organic. The gap we have, and that's for researchers who want to work in this area, the gap exists between 390 degrees up to 500, 600 degrees. This gap is filled at the moment with mercury. And mercury is not a fluid you want to work with. If researchers can come up with a fluid that is really stable in this range, let's say from 400 to 600 degrees, that will be the holy grail. That will be really the holy grail. And of course, looking at azeotropic, azeotropic scenarios where you can build fluids, there is a huge gap. Not only for heat pipes, the heat transfer fluids in general, in particular, in concentrated solar filters. They're using molten salt this morning. But if you come up with a fluid that is safer, cheaper, that would be a really good earner. Thank you for the question.
Okay, question?
Thank you. Actually, when I look at your applications, I see actually you perform very commercial applications in England. And here I wanna actually, while you are talking about the heat pipe, you said that we use the high temperature heat pipe for the applications. What about the low temperature? For example, we can we use the heat pipe for cryogenic hydrogen applications? What do you see? What do you think about that? Thank you.
Thank you for the question. And I only showed here this area because it's an area that is highly interested in. If you come and visit my lab, for example, we have cryogenic heat pipes that go down to minus 170 degrees. The project is funded by a company called Air Products. The application is in bio. And for that, we use a combination of working fluid that is suitable for that environment and specific thermal materials. So if, for example, we use the cooling and technique, for instance, we have to interpret the back. So we have that scenario. The TRL level is still low, but we have one area where the TRL level is higher, given the company is making it. We only deal with commercials at the end of the research, obviously. So that's what we have. I started my work in heat pipes with HVAC system. So the HVAC system that you have here, if you go to the UAE or South Europe or India, I have systems that have my whole shoot. That's what I started. And for those environments where the temperature, working temperature is between minus 30 degrees to plus 60. In the old days, we used to use R11 fans, then R22 R134A now, that it is being phased out. So there is always work on what is placed in. For those temperature regions, we have to find suitable figures. So at the moment, we're working with a refrigerant that is being used in the car industry, which is proving to be a good replacement for R124. But because R124A is not totally phased out yet, we are still afraid. But we have to think about the next step. Thank you for your question. For cryogenics, absolutely, but different challenges. The low temperature ones, you have to think about refrigeration from minus 40 to minus 50, all the way to plus 60. We can push it to plus 70. We use copper mainly for the swimming.
Many thanks for your presentation. I would like to ask about the pressure of the water inside the pump. Because as you know, the supercritical temperature, at the supercritical point, the temperature of the water is about 374 degrees Celsius. So I guess it's not too high, but what about the pressure inside the pipe?
We don't treat it 100% there. The pressure inside the heat pipe is always saturated. Always. So when I say the inside temperature limit for heat pipe with water at 300 degrees, that is 300 degrees saturation at 86 bar. The pressure inside is 86 bar maximum. I don't go beyond that. If I go beyond that, up to 310, maybe during short periods, fluctuates. But 300 degrees is the maximum, 86 bar. And I design, so there are scenarios where we do heat pipes of customized shape, so we end up having pressure relief valve. The pressure relief valve is usually raised 110 bar. So, but below 300, always the case, whatever the temperature is inside corresponds to the saturation temperature of it. So when you have a heat pipe running at 100 degrees, you can imagine the RG is zero. It's atmosphere. What I say, one point there. So the RG is zero. Anything below 100 is basically lower than that. So that's always saturation. It's very interesting. Thank you.
If there is no further question, oh, thanks, okay.
Thank you, Professor, for such nice presentation. I just have a small question. How you are going to capture this heat from flue gases? Let's say, for example, you have the flue gases that's come out from combustion or something else. Yeah. So the gases that's come out from the combustion, like flue gases, so they are typically at very high temperature, and they are more corrosive in nature. So are you using any pre-scrubber to first scrub them out, the harmful effluents, and then you are taking the heat to the your heat pipes, or it is directly exchanging the heat to the surface of the heat pipe, because that is very corrosive environment. So what is the outside of your heat pipe? I'm most interested in the material that you are using, or are you seeing any effect of that if you're using it for such kind of application for carbon capture or something like that? Maybe. I sorry, I came a little bit late. Yeah.
So the idea project, the idea is that they structure. So this design, in a way, condense whatever you have in the blueberry, whatever assets you have, to condense it inside the heat pipe itself and make the heat pipe out of metal that will withstand the corrosion effect. So that's really what the hydro process is about. That's what we are doing with regards to installing what we call them as heat pipe condenser equipment. You're pushing what we have it for sensible heat exchangers where, but for those who design them to stay above the 2.4.
Okay. Fair enough. Thank you.
I think you just missed the last few slides.
Yeah, I just went out. Okay. Thank you.
Is that
Yeah, it's fine.
unless I misunderstood the question?
Probably we can discuss more later on. Okay. Thank you. Yeah.
Then let's thank our keynote speaker once again.
And Professor, before you leave, can I invite Professor Dr. Zafer Utlu in order to give you your token of appreciation? Once again, our sincere thanks to Professor Hussam Juhara for his valuable contribution. Thank you, Professor.
Thank you. Thank you very much.
We will now continue with our second distinguished keynote speaker, Professor Dr. Nevin Duik. Professor Nevin Duik is a distinguished academic at the University of Zagreb. His research focuses on energy systems, renewable energy, sustainable development, energy system modeling, smart energy systems, and the transition toward low-carbon energy system. He has participated in numerous European and international research projects in sustainable energy planning and renewable energy integration. The title of his keynote presentation is The Role of Electricity Storage, Demand Response, and Molecular Storage in Smart Energy Systems. Professor Duik, we are delighted to welcome you to the WESC 2026, and the floor is yours.
Hello, everybody. It's great to be here. We are, let me see, we are on the cusp of energy revolution. Those alternative variable renewable energy sources are already cheapest for 10 years to install, and they are going to continue to be the cheapest. And already for some years, most of new technologies in power production installed on a global scale are wind and solar, which bring us, thank you, which bring us to the point that wind and solar in Europe are already overtaking fossil fuels. Renewables made 50% of electricity production in Europe, and fossil fuels only 25%. And on the global level, solar has overtaken nuclear. So we are going to be solving energy systems in completely different way. But some countries are more advanced. There are territories, energy systems, which already run on more than 100% variable renewable energy. Like, for example, a Brazilian state of Rio Grande do Norte with 300% of wind. They didn't have any wind or any local production of electricity 10 years ago, and then in 4 years they built 300%. They were importing cheap hydro from Pará, neighboring states, and then now they are exporting wind. So how did they do that? They say it's not possible, but many countries manage to do. Everything above 20% of wind penetration means that you need some kind of technologies to resolve it. You can, of course, export it, but most countries will have to store excess energy in some hours somewhere. On solar side, we have a functioning power system, which is more or less 100% solar. Tokelau, it's a small system, but if you build a small system, you can also build the big system. There is no big difference between the small one or the big one, apart from having to invest into more technology. And we have quite a few countries, and some of them very poor countries, which have very high share of solar energy. That means it works also in war-ravaged countries like Yemen, for example. Everything above 10% means you need to have some storage or some solution for excess of solar when the duck curve occurs. So let's look at what happens when you have a normal power system with the black one being the base load, usually coal or nuclear, and then you have intermediate and peak load, which is the blue one, which is usually hydro or gas. And then we put like 25% of wind and solar into this power system. So wind usually pushes all other power plants from the merit order during the night, and solar does it during the day. So you have only remaining power plants working in the morning and in the evening. What happens with the excess? Well, you can export it, but other countries around you will have most probably the same problem. They're also invested in wind and solar. You can store it, but why would you use fossil fuels to store it? So the cheapest thing at this level is just not to produce it, to shut down your baseload power plants. But that kills economics of coal and later nuclear. Can actually batteries solve variability problem? Partially yes, but fully only in countries between 35 degrees north and 35 degrees south, so the solar belt countries, where seasonal variability of solar insolation is less than 3. But if you go more north from that, and Europe is more north from that, you need to add wind into the mix, because in winter you just don't have enough solar energy. In Croatia, the difference between wind and summer is 7 times. In Denmark, it's 10 times. So you would have to be overbuilding solar 7 to 10 times in order to cover everything from solar. So adding wind is cheaper. The problem with wind is that wind has weekly periods So the batteries cannot solve it. You would need 140 hours batteries, and we have now 10 hours batteries. And I don't think that 140 hours batteries will become viable that soon. So if we are not looking at these solar belt countries where everything can be solved easily already, and if we look at those moderate climate areas like Europe, China, North America, then the solutions are more complicated. We need, of course, more grid interconnections because variable renewables are not behaving the same way everywhere. So you can export part of the problem and get import part of the solution. You need to flexibilize thermal power plants so they can follow your variable renewables. You need wholesale markets to make it cheap. And the most important thing, you need demand response and integration of power, heating, cooling, transport, water, fuel feedstocks and industry systems, or something we call smart energy systems or power to X. So most of the storage will actually be outside of the power system because it's much cheaper to store something else than electricity. Of course, we will need dedicated electricity storage, but it's a quite expensive one. So let's look at interconnections. If we look at variability of wind on a small country like Netherlands, the pale blue line, wind is very variable. But if we look at the European level, it's much less variable. So if we look at the last 8 years, there was not an hour without wind in Europe. If we look at the part of the wind under the red line, this could be called a baseload wind. So it's blowing somewhere up to a certain level all the time during the last 8 years. So yes, Dunkelflaute happens, but it's local. If you have enough interconnectors, you can easily bring electricity from other areas. The big question is, what do you do with this wind above the red line? Well, that one can then be used somewhere else. It's free energy in a way, but we'll come to that later. What about cycling thermal power plants? They're already cycling. This is German hard coal power plants in July 25. So they're basically turning off and on twice a day. There is no more baseload in Europe. There is no such concept anymore for thermal power plants. They're just all cycling all the time. It's technically interesting problem. It can be done, of course. And China has decided to completely use coal power plants to balance wind and solar because they don't have gas. It can be done. But you're not going to be build any more new coal power plants in Europe because the economics is too bad for that. What about nuclear power plants? They started to cycle. Well, now they're shutting down because of not enough water for cooling, but this is a normal May. So they were not having problems of cooling like now. They were just cycling because there was excess of wind and solar. So who is going to be building nuclear power plants if they don't have 8,000 hours in the market? Well, of course, governments will have another reason to build nuclear power plants because this is a dual technology. You need them for something else. And if you build them, we can integrate them. But in the power market, they will be only filling the gaps in between variable renewables. And the rest of time, they will probably be producing hydrogen. What happens is when you have a high share of solar and wind in the power system, the electricity price goes negative or very low. When the electricity price is under 20 euros per megawatt hour, which happens now quite often, then electricity is cheaper on the heating value than biomass, than wood. And it makes sense to use it for heating or for any other purpose outside of the power sector. So what we are looking now is a fast electrification of everything. Turkey has put a very high goal on electrification of energy systems as a president of the next COP meeting, which I think is a very good goal. And the European Union is following with its own goal for electrification. Electrification is finally coming. And why it is coming? Because electricity has negative prices in many hours. We can look at Europe, it's just exploding. Especially in countries with nuclear power, then you get a lot of negative prices electricity. So what can you do with a negative price of electricity? It means if you can destroy electricity and make money on it, you are going to make money on it because you are going to be paid to take this electricity. Can you convert it into heat? Well, this is obvious first solution. Look at South Australia. It has 25% of negative prices during the year. So one solution that Danish have developed is to install electric boilers and heat pumps in their district heating systems. They need to heat their houses for more than 6 months a year, and they also produce hot water. So this is a very common system in Northern and Eastern Europe and in China, district heating. So whenever electricity price is low and the spot price is pale blue line, then you have electric boilers or heat pumps or both converting this cheap electricity to heat and storing it. This is heat storage. Whenever electricity price is high, then it makes sense to produce electricity using gas CHP units, which also produce heat. So district heating is becoming a very variable installation, which can either use electricity from the market if it's cheap, or if it's expensive, then produce it and sell it on the markets. Also, electric cars are coming. Global sales last year were 24%. Now, because of the Hormuz crisis, the sales are exploding. In developing countries also, this is a new phenomena. In Turkey, I'm very glad to see that I can now charge my Tesla when I come next time everywhere. I was walking yesterday around and there were electric chargers really everywhere. And this is creating a situation. So try to imagine the following thing. Everybody has a 7 kilowatts charger at home, for example. And everybody comes at home at 5 p.m. And in Austria, let's say they would have like 4 million cars. Everybody plugs in, and that would be like 28 gigawatt at the same time in a country that has 14 gigawatt of installed capacity. Of course, it will not happen like that. Not everybody will come at home at the same time, but we are going to have a problem of charging. So we need smart charging. Instead of stupid charging, you plug in, you get electricity. Smart charging, which charges your car when electricity is free, like during the night or during the day. And there will be many hours where electricity will be practically free. So what is optimal for smart energy systems? Charging price should be based on time of use coupled to wholesale electricity price. This is already implemented in Western Europe. Basically, you can opt for such a tariff in which your electricity price changes every 15 minutes according to the wholesale price. So you can charge basically for free if your app is controlling the charging process. Of course, you have to pay the network fee. but the energy is free at those times, or even negative price. Even you get paid for it. Every parking should have a slow smart charger because we are parked 90% of time, and our cars could actually help variable renewables get integrated in the power system. It's a lot of energy. Cars will need at least 40% more electricity than we are using now. So this is significant. And fast chargers should be used only on long distance trips, and everything should be app controlled, maybe AI control. We'll see how it works. We did many years ago a simulation of Dubrovnik zone, which is a region in Croatia, to see can we charge cars only using excess wind. There is a lot of wind there. And we measured how much cars are actually spending there, driving per day when they are parked. And it came out, this green is energy needed to cover personal cars in Dubrovnik area. And yes, they can be charged only during times of excess wind. So this is feasible. Power to buildings. Buildings consume a lot of energy, and this energy is going to be electrified. We're not going to be heating on gas boilers or woods in the future, maybe on wood in some rural areas. But in cities, we don't want this pollution, NOx, and etc. So buildings will need storage. They can serve as storage themselves, but we will need additional storage in heat called hot water storage, which is cheaper than batteries but takes more space. So space here will become an issue. If you have a small apartment, you don't have 4 cubic meters for storing heat. But if you have a house, you have. But then the building might have a lot of area in the underground, which is not really used. And it could be used by the whole building. Or even better, we could have a district heating and cooling, and everything could be stored on a installation site. So there are many possible solutions for that. Electricity price based on time of use coupled to wholesale electricity price. Again, if we use that, we can basically heat and cool for free. Because electricity energy part of the electricity price will be often very cheap or even free or even negative. Solar rooftops will depend on net metering tariffs, but the storage can also be used to capture this excess of electricity produced on your roof. So let's go to see how this will influence, for example, wind integration. The black line, we can see if we increase the share of wind, then critical excess of electricity production is increasing. And at 5% of excess, it stops being economic to push further the share of wind. So that is this magical 20% limit of economic integration of wind energy. But if we couple wind with heating, then we can increase that to 40%. This is what Danish have already implemented. Power to heat and your variable renewables can be better integrated. If you add transport, you get to 80% of power can be supplied by wind only, and the excess wind is used to decarbonize heating and transport. So the future energy system will simplified look something like this. We will overbuild. This is non-solar belt areas, so north of 35 degrees. we will overbuild wind and solar 3 times more than electricity we need today. And that will cover more or less our legacy electricity demand that we have today. We will electrify transport and cover it by the excess electricity, but with smart charging. We will cover the heating and cooling with smart storage that will use wind and solar energy. And there will be a lot of energy for hydrogen and hydrogen-based fuels and feedstocks. So coming to hydrogen, which way hydrogen will develop? Is it going to develop? Well, there were 2 narratives a few years ago when the second hype of hydrogen was starting. And I'm very old, so I did participate in the first hydrogen hype. I built the second on-grid green hydrogen power plant in the world on the island of Porto Santo. We started working on it in 1998 when the first hydrogen hype started, and built it in, finally connected to the grid in 2007 when it was already finished. So it was decommissioned after 1 year of working because nobody was interested in hydrogen. And now the second hydrogen hype, there were 2 narratives. One was decarbonize gas and fuel by replacing it with hydrogen and synthetic fuels. And the other one was only hard to decarbonize sectors where other alternatives might not be feasible or have higher costs. So let's look which of those 2 narratives is correct. If we look at power to e-fuels for heating or power to hydrogen for heating, we needed around 5 petawatt hours of heating in 2015 in Europe. So with heat pumps and COP3, that would be around 1.6 petawatt hours of wind and solar, considering that we are going to build our future energy system on wind and solar as we are doing now. But if we go to hydrogen heating, then we need like 6 or 7 times more wind and solar. We don't have that much space to waste so much energy on hydrogen heating. So it will just not happen. It's not efficient enough. Hydrogen is something that is too valuable to burn it on in gas boilers. Even natural gas is too valuable to burn it on in gas boilers because the exergy destruction is huge when you do that. It's only 15% exergy efficiency. So let's don't do that. What about transport? It's a little bit better situation. If we power everything directly with electricity, we need 4.5 petawatt hours. If we power everything with hydrogen, we need double, around 9 petawatt hours. With synthetic fuels, it's 24 petawatt hours. The problem here is probably not so much efficiency, it's more the infrastructure. We would have to build hydrogen infrastructure from scratch, and we already have electricity infrastructure. I'm driving electric cars everywhere. I did already 5 continents. I went with my Tesla to Asia and to Africa, and there is electricity everywhere. You just plug in, you have no problem. Chargers are, of course, nice thing, but you can charge everywhere. So I think electricity has won in transport also. But what about the rest? Shipping, long-distance shipping is something we cannot electrify, most probably. And what seems to be happening is that shipping industry is moving towards ammonia or methanol. Aviation is moving towards sustainable aviation fuel, which is using carbon from biomass at the moment, mostly waste cooking oil, and then hydrogen to bring it to the kerosene level. Fertilizers, we need hydrogen or ammonia. Metal smelters, electricity or hydrogen will most probably be a solution. Steel mills, if you use recycled steel, it will be electricity. Cement and lime, hydrogen or maybe electrification. I'll come to that later. Chemical industry will be based on methanol economy, and other industry mostly electricity. So it's time for new technologies. It's great time for engineers. There will be a lot of work. And here we can see where we expect that hydrogen and its fuels will take place, and this part is already more or less moving to electrification. And let's look at the cement industry, a very hard issue. Pre-calciner or calciner part of the cement, where we break down CaCO3 into CaO and CO2, is something that needs high temperature. This high temperature can be provided by very hot air, which can be produced by electricity. And then we have already heat storage that goes up to 1,500. And we need heat of 1,000 degrees. So we could use heat storage. Bricks, for example, that could store heat. So whenever we have cheap renewables, we use hot air to produce CaO. And then when we don't, and we also store it in heat storage. And when we don't have it, we use hot air from heat storage. For the kiln is more complicated because the temperature here is 1,600. We can still do direct electrification using hot air, but we still don't have storage that could go. We would probably need 2,500 storage, but I guess in a few years' time we will find solutions. When we look at the cost of hydrogen, if we can consider that by 2030 the capex of electrolyzer will fall down to $350 per kilowatt, then we can see that solar only in Europe will not work, because we have 1,000 few hundred hours of solar, and that makes it quite expensive. So we need a combination of wind and solar in Europe. But in Chile, which has Atacama 3,500 hours of solar hydrogen is probably feasible. And then taking into account all these calculations, we can see what are the best areas where we can expect hydrogen to be cheapest to produce. Atacama, as I said, Patagonia, parts of Sahara. Turkey is not doing bad compared to Europe. Europe is very bad. So Europe will have to, well, we can still produce it, but it will be more expensive. So we will have to import hydrogen. And European Union says we want to have international hydrogen trade, but what about liquid hydrogen copying the liquid natural gas, methane? Well, liquefaction losses of are 3 times higher than LNG. We lose around 33% of energy by liquefying hydrogen, and then there is a 1% daily boil off. So this will probably not work. It will be easier to convert it to ammonia and then ship it, because ammonia is good as a fuel for ships, and also we need a lot of ammonia for production of fertilizers. I think around 5 or 7% of global CO2 is coming from ammonia. So the question will be, why not exporting feedstocks, fuels, and products like fertilizers instead of hydrogen? Okay, let's compare various options. If we export hydrogen by ships and then convert it back to electricity, we get 26% cycle efficiency. If we do it with ammonia, it's even worse, 23%. If we export directly electricity, is 82%. So if we are going to export electricity from other areas, we're going to do it with cables. Cables are feasible even between the continents. It's a geopolitical reason why we're still not building them. Of course, from South America, we will not build cables. We will most probably not export hydrogen. We will most probably export ammonia or fertilizers themselves. Ammonia doesn't make sense to convert back to electricity. So there is a limit to trade in ammonia, only to cover ammonia needs, global needs. And this is what is expected by IRENA. I'm not sure I fully agree, but they think that methanol and ammonia will become a significant trade. Hydrogen by pipe, of course, lots of electricity and lots of bioenergy because we need carbon to produce methanol. And exporting areas will be Latin America and Middle East, and importing areas will be East Asia and Europe. And then short insight into future methanol economy. So methanol is expected to become a main feedstock of all the chemical industry because you can mostly produce everything from methanol. So methanol, which will be produced from renewable hydrogen and renewable carbon. Renewable carbon coming primarily from biomass. Most probably we will use this biomass for some energy purposes, burn it, and then use CO2 and hydrogen to produce methanol. And then we can produce anything we need later on. So few remaining spots. How are we going to solve the problem of reserves? We will need lots of reserves, primary, secondary, tertiary reserve to have our system have stable frequency. Well, demand response can provide unlimited amount of reserve. Danish are using electrical boilers. Electrical boilers are very fast. So you can just turn them on and off when you need to provide reserve. You don't need to necessarily have a power plant to do that. Gas power plant is very old way of doing it. Batteries, it's another system, of course. But demand response can be a huge provider of reserves. We will need backup. That's for sure, because Dunkelflaute does happen on a continental level. The last time it happened was 2009. And when you have a Dunkelflaute for 2 weeks, then you need some kind of backup. And the cheapest solution is the gas turbine or gas engine. We already have them all built. We have all the gas storage we need. So just question to have a little bit of gas waiting for such a situation. And we can convert from fossil gas to biogas or biomethane. We will also need to solve the problem of reactive power in order to have voltage control, and grid forming inverters are a solution for that. I hope Spanish will learn from their mistake, because they didn't force the inverters to provide reactive power, and that's why I had this blackout. We will also need inertia. Without spinning power plants, spinning generators, we don't have inertia in the system, and that's what provides the frequency support during these few seconds before the primary reserve can turn on. And the one possible solution that we implemented like 20 years ago in Azores was to use idle generator. You connect it to the grid and let it turn without providing active energy. It just provides inertia. Or you can have you can produce synthetic inertia based on batteries. Coming slowly towards conclusions, wind and solar-based energy systems in moderate latitudes need smart energy systems. That means integration of power, heating, cooling, transport, water, and industry. Batteries in electric cars and standalone will be a huge solution, but not only one. Hydrogen, mostly for fuels and feedstocks, sustainable aviation fuel, ammonia, methanol, and for reduction. And it's easier to store hydrogen and cheaper than electricity, but not very easy. So it's easier to stop to store the feedstocks, which are liquid, like ammonia or methanol. And then heat storage will be huge. It's cheap, even at high temperature. If you take bricks, it's really not a big deal. My research is energy planning. As you probably know, that I'm editor in energy, and my topic that I cover is energy planning tools. And this is H2RES, which is energy planning tool that we develop. It's open source, Python. So you can download it and you can play with putting all these technologies together. If you want to know what will come in the future, you have to calculate it. And energy planning tools are the best way to know what happens in 5, 10, 20 years' time. And we have a competition that says if you manage to model your country with 100% renewable supply with certain conditions, then you get a fee waiver at one of our future conferences. We are organizing this Davis conference series. Thank you very much.
Thank you. Very interesting and timely talk. About 7 years ago, I think we talked about the UK and Europe because I'm quite familiar with them. Many of peak shaving, energy planning, smart charging, smart tariffs have been implemented. And now, if you go to the UK, for example, a substantial number of homes, I would say over 70%, they're already using smart tariffs. Not forced to, but they want to, because, for example, you pay 7 pence from 11 o'clock to 6 o'clock in the morning compared to 33 pence during the day. So obviously people want to save money doing nothing. So what they do now, they shift the demand voluntarily to off-peak. So this is a human behavioral thing, I believe, is what is missing. The infrastructure exists and we have it. Of course, we'll be improving on it, that goes without saying. But I believe the missing element is the human factor. How do we educate people to actually make use of that, which is good for them? What is the best way? People say it's a human behavior about comfort. They want to be comfortable. They want to be convenient behavior. I think that is the area where engineers are actually struggling to get to, because it's really more about human behavior. What are your thoughts on this? And how can we communicate that to people so everyone understands the message? The second point about the next generation electric vehicles. The next one now, for example, you can plug your EV and it interacts with the grid. It actually sells the energy back if you agree to it. So your car becomes like a battery connected to the grid. So this is now there. It has been there for the last 2 years. I believe that will grow further. again, that's something maybe just want to mention because you present some very interesting facts there. And the last thing about hydrogen, do you think the topic is now cooling down? When I was here 2 years ago, it was extremely hot topic. Now things are changing. So I hope you can give us answers for these three questions.
Thank you
Thank
for excellent questions. I'm very pessimistic about changing human behavior. I don't believe in it. 5% of people will switch on and off demand because of any reason, even the price. So the solution have to be 100% technical. And that's why I'm saying up. You plug in your car into electricity when you come home, but the app decides when to charge it. And only significant demands at your home are your electric car and your heat and cooling system if you have storage. So everything else doesn't really matter. But these two should be governed by app. And then whatever you should be deciding is no more than, okay, I want to have at least 10% of electricity in my car so I can go to the hospital if something happens. Or tomorrow morning I go for a long trip, I want to have it 100%. But you don't want to decide anything more than that. Regarding the second question was about, the third one was about hydrogen. What vehicle to grid? Yes, vehicle to grid depends on economics. Battery in your car is part of the car. So if it's cheaper to use it because you're wasting your car by wasting your battery, then having a stationary battery whose capex is only the battery, then you're going to use the car. So if your car battery is 150,000 kilometers, you're not going to do vehicle to grid. But if your car battery is 600,000 kilometers and you're driving it only for 300,000 kilometers normally, then it makes sense to do vehicle to grid with this additional 300,000 kilometers. And new batteries that are coming on the market have this prolonged life. So I think there might be economics in that. But up to now, there was no economics because you would reduce the value of your car. Regarding hydrogen, I was a bit sorry that it happened a few years too early, the second hype. Now it's having all the bad tales coming because hydrogen is coming, but that was induced by gas lobby that they want to protect their pipelines, and it was not yet ready to for the real hydrogen coming. Real hydrogen coming is when we are going to have huge amounts of variable renewables on the grid, which we are starting to have. And we are already going to satisfy quite a lot of electricity to heating demand and electrification of cars. Only after that, the hydrogen is really coming. So I would expect that real hydrogen time is 2035 from my energy planning conclusions. So it's coming, but now it's cooling down, yes. Thank you.
Thank you, Dr. Duic. Actually, I will ask about you said the real hydrogen is coming. I agree with you. You said actually it is mainly based on the renewable energy, renewable electricity. Okay, so you said that it will coming 2035, you said. So at that time, it is quite difficult to establish the small modular nuclear reactors in the Europe. I believe that the Europe pay more attention for establishing, for designing the small modular reactors and other type of the reactors. When they finished all the installation of the small modular reactors in the Europe, I believe that it will really coming around 2040 or 2045. What do you think?
Well, you have supply side and you have demand side. So I was talking about demand side when it will be actually cheaper to produce hydrogen from excess of renewables in order to feed it to the industry. But on the supply side, I could agree that your linkage with nuclear makes sense. But I would put a certain caveat here also. There is now a nuclear hype coming. Some of it makes sense because in the general climate of insecurity, I understand that governments want to build a bomb. That's the only reason why you would want to have a nuclear power plant, because you need nuclear power plant to finance all the system that is needed for fuel handling for the bomb. You are not going to build nuclear power plants from the energy point of view. It doesn't make any sense. Nuclear is 5 times more expensive than renewables, and 2 times more expensive than renewables with all the storage and all the demand response and everything. So it only makes sense if the government has a security reason to build the nuclear power plant, which I understand. No problem. If that is political decision, I support it. I believe that security is an important issue. And if we want to do that, okay, we as engineers can integrate this power into the system. And as you said, probably around 5,000 hours of electricity will be sold to the market because it will be able to compete in 5,000 hours with solar and wind. And other part of the year, 3,500 hours, it will be producing hydrogen. So in that sense, I agree with you. On the time of arrival of small modular reactors, I'm not so optimistic. It's technology that doesn't exist yet. It takes 20, 30 years to develop new generation of nuclear power plants. And it takes around 25 years to build nuclear power plant with known technology. If you look at Olkiluoto or Flamanville or Hinkley Point, all these projects are 25 years between decision to start developing them to connecting them to grid. So the time span for new nuclear power plants will probably be longer. It can be made faster. We have Chinese example, but this is very different context. You need to have a serial system where you build same power plants every year, new one. So you have engineers. We don't have engineers. We stopped teaching nuclear technology in 1990s in Croatia because we decided there will be no need in the market. And many other universities have stopped teaching that. Now we have to restart that. It takes 10 years to build engineers. If we still have knowledge to teach them, we fortunately probably have. I'm an engineer who was taught nuclear technology, but I'm very old now. So my younger colleagues, they have no idea about it. So I don't know.
Sorry for taking follow up, but I hope I can disagree with you politely, if that's okay. I fully disagree with everything you said about the nuclear industry side. I do apologize for this strong statement. I don't think anyone who wants to build a nuclear power plant are after the bomb. They both work in different way, different technologies, different requirements. And I'm sure you know that, having studied nuclear engineering. I'm a nuclear engineer myself. We are teaching nuclear engineers in many universities in the UK. I'm sure across Europe also. So it is quite healthy when it comes to training engineers. SMR is well-developed technology also. We collaborate with Rolls-Royce, and they're actually making really good advances on SMRs, 50 megawatt. The plan is for 50 megawatt, and the idea is to localize the SMRs where energy demand is within that range, so you can have the flexibility. I don't think it will take 20 years. I really don't think so. The nuclear energy is key for the baseload, and I think you kindly showed the baseload values. So in the UK, for example, we have 5%, which is provided by nuclear. Unlike other power plants, you can't really just increase and decrease the load, as you know. You have to keep it steady. That's how nuclear energy works. Having steady output, meaning that's your base load, 5% is always there. Whatever goes after with the fluctuation is basically provided for by fossil fuel. And then when having the integration with the renewable sources, as you have kindly said, yes, you need the smart systems. So my interjection here, I hope you don't mind me just stating that fact, because I am very much involved in this one here. It's actually much rosier than you put it. We have really good plans for nuclear power plants. In the UK, we are building one, as you will know. In Germany, they are restarting an old one that was stopped because there is a demand for it from the point of view of AI use. So there are lots of movements now to bring the nuclear energy back. It is a safe technology if you know how you do it. Of course, it comes with caveat. It comes with, like you put it, if you don't have the infrastructure, technological infrastructure, then the safety aspect is a problem. And I hope you don't mind me just interjecting here. I'm sure it's complementing what you're trying to say, but I do believe that having a baseload design on nuclear energy in the long run is a safe and healthy approach for governments. Even if I agree with you with the 25 years, which I don't think it is the case, still, for governments, they need to plan for the next generation. I hope you don't mind my interjection. Thank you very much.
Thank you. I would politely agree with you that not all building nuclear power plants want to build a bomb, but this is not what I said. I said that the only sense of building a nuclear power plant is if you want to build a bomb, because baseload doesn't make sense. And then I must say, you probably didn't listen to my lecture, because I was lecturing about the end of baseload. You can't have a baseload if you have wind and solar, because wind and solar are going to take a full load in 4,000 hours a year. So you don't have a base load. You need flexible load, you need demand response, you need storage, but absolutely no base load. Base load is a dead technology. Sorry, politely. Thank you. Thank you.
Thank you. Thank you, Professor. Could you please keep you on the stage? So I would kindly like to invite Professor Ibrahim Dincher to present the plaque of appreciation and recognition for your valuable contributions to the conference. Thank you very much, Professor. Dear Professor, can we keep you on stage also, Ibrahim Hocam? So I would now like to invite our third distinguished keynote speakers, Professor Dr. Ibrahim Dincher. Professor Ibrahim Dincher is a professor at Ontario Tech University in Canada and director of the Clean Energy Research Laboratory. His internationally recognized research covers thermodynamics, energy and exergy analysis, renewable energy systems, hydrogen technologies, fuel cells, thermal energy storage, and sustainable energy systems. Professor Dinçe will deliver his keynote presentation entitled Deconsumption and Energy Storage for Sustainable Development. Professor Dinçe, is a great honor and pleasure to have you with us at WESC 2026. The floor is yours.
Thank you. All right. Probably is now afternoon. Good afternoon, everyone. I am really delighted to be here. Before my talk, I like to thank the organizers and the university really making this event really successful and bringing all of us here today to share really what is happening in the field. And so the talk is going to be really about the consumption, because there are a couple of things I like to highlight in my presentation. One is going to be really the consumption. So that is something very critical. And also I will take you to energy storage along with the sustainable development. So let's proceed. Of course, quickly to see, centuries, to be able to highlight the importance of energy. And what we see here, really energy consumption per person and increasing really exponentially. And this is really clear. And eventually the future, of course, by 2050, and where we have really, let's say, synthetic humans, being even part of this process. So really energy demand has increased and will continue increasing. So looking at the energy consumption, this is based on the figures in 2024 and clearly seeing, certain specific countries really per person or per capita really leading, and clearly you see it, number one is Iceland, followed by Qatar. So really to give you an idea, but what is really interesting here to illustrate, especially this, on average, one American consumes as much energy as, this is giving you an idea in terms of really how many Japanese, how many Mexicans, Chinese, Indians, and so on and so forth. So really making it very diverse. And you see it over the world, really energy consumption per capita is quite diverse. And one thing is very interesting, global CO2 emissions, how much contribution comes from the energy sector. This is something very interesting. I like to highlight it. And this is not by me, by the United Nations, by basically. So published a report basically back to 2024, and saying that energy sector has contributed by 68%. Imagine year after published a report, you see in 2025, and indicating that now the contribution is really about 73%. So imagine during that period what has happened, and the decarbonization efforts, of course, have taken place, but the reality, you see, 5% increase. This is globally and by really energy sector. And I'm not going really through in terms of to show, what is covered, you see from transportation to industrial and agricultural sectors, you see all are really covered in it. And the point here, really, I like to bring it down to this equation. This is something very critical. In everything, we see 3S. And this is, of course, source, system, service. And I see it for anything, everything, you need a source. And then really, accordingly, you need useful outputs. Really, I treat them under service. Now, accordingly, you develop your systems
and really design them and implement them accordingly to be able to cover your needs. And there are, of course, two more S into this. And as you see here, between source and system, and why energy storage is going to be needed. Technically, imagine you have, of course, as mentioned earlier by the keynote speakers, that imagine you have, of course, solar, the sun and wind really not available all the time, fluctuating. So what is needed? And when you have your system, of course, you need to really operate steadily, and that is going to require storage here. And then also storage is going to be needed right after the system. Imagine if you produce more than what you need, or you need to store it in either electricity or thermal heat or cooling, so you need to look after it. So storage is becoming very critical in this equation as well. So obviously, if we are going to really target to achieve sustainability, we need to look after this. And in terms of dimensions of sustainability, really, I bring them down to this E, basically. And we have these E's are becoming very critical. Energy, exergy, of course, Professor Deutsch mentioned about it. And really very critical, especially, is going to be coming down to system design, analysis, and assessment. And really a very critical tool, education, engineering, economy, environment, and ethics. And ethics is something very critical, especially coming down to individuals and institutions. So really, without ethical responsibilities, individually and institutionally, really not being able to achieve sustainability. And then in here also quickly listed several, of course, sort of solutions or prescription. And, really from changing lifestyle and habits, this is something by Professor Johara mentioned or asked about, human behavior. This is something very critical coming down to, of course, changing lifestyle and habits, and which is, of course, very difficult for people to change. But anyway, so there are so many things listed here, but the key, really, what is important, we need to implement right energy strategies and policies. And also at the same time, we need to keep in mind energy solutions are like drugs. And do you know any drug without any side effect? No. So similarly, whichever energy solution you pick, there will be some side effects. So obviously, this is something we always need to keep in mind. And then now in here, what about the prescription? Getting a right prescription. What we do always, really trying to find experts or specialists to be able to get right prescription for cure. And similarly, we should do it for energy solutions to get right prescription. And also, of course, the way we really look at this, now the problem is really beyond like taking a painkiller. So we need to do infrastructural changes. And also, of course, this is taking us further to show we need to change our energy diet. And this is something really into a more healthy energy diet. Regarding the question here, is it really about decarbonization or recarbonization? So, and this is the point I like to raise. Of course, we are going to really end the period of fossil carbonization, but biocarbonization will always be there. And that's why we need to change it into biocarbonization. So people talk about a carbon-free society, and carbon-free society is not possible. Is not possible to survive under. So that's why it is biocarbonization. And we need biosources, as you see here, several examples. And also the question, decarbonization versus the consumption. And this is something very critical to highlight. And when you look at here, of course, the main issue, the example over there by the United Nations report, and showing that although there have been efforts really to decarbonize, but reality is not being decarbonized. So there is something wrong, and that is coming down to overconsumption. And look at this, and that's why we cannot achieve sustainability without really the consumption. So that's why even this, I don't like it, consumers, and of course, to have a client is better. So this is something very interesting. And also, I like to show a couple of quick examples to move into my real subject. And this is to clearly illustrate, even you see here, a standard, let's say, T-shirt, and which is going to be, let's say, around 175 grams. And then you see how much CO2 it generates, and then how much water is consumed, and then how much electricity is consumed. And if you look at it, it's going to be really 2,700 kilograms of water consumed for one simple t-shirt. And then look at the CO2 levels, around 11 kilograms. And also look at the energy consumption. And these are giving you an idea. And also what is interesting by Europe to be able to show, and look at this is again by the European Union, and how much consumption per person in Europe in terms of textile. And this is also, you see, per year, 15 kilograms on average. This is something. So that's why the problem is consumption. So excessive consumption or consumption habits are really driving this unsustainability or non-sustainability. So we need clean energy solutions. If you look at here, what people need clean air, clean water, clean food, and clean energy. So clean energy, of course, we need renewable energy technologies, hydrogen energy technologies, green fuel or clean fuel technologies, efficient energy use, cleaner technologies for fossil fuels, energy storage technologies, nuclear energy, and the waste to energy or waste valorization, system integration, and multi-generation. These are becoming really critical under this clean energy portfolio. So I like to, of course, take you into this energy storage. And of course, we need to look at the options. And of course, we have mechanical energy storage. And people are familiar, you are familiar with, from pump hydro to compressed air storage. Thermal energy storage, commonly, of course, we have sensible and latent. Chemical energy storage, of course, in various forms. And also, of course, hydrogen is going to be there. What you do, you, as mentioned, you have excess power. What you do, you produce hydrogen, store it, and use it later when needed. And then electrochemical energy storage using, of course, batteries, flow batteries, and also magnetic and electromagnetic energy storage, and even biological, and you may have it through biofuels, fats, etc. And that's why we human beings also, we have our own energy storage, and we have some fat around us, around the belly, and that's what the reality is. So really, when you look at this, also to be able to see the evolution, and you see started in, of course, early 70s, and then with basic thermal energy storage systems, mainly hot storage,
hot water storage. And then now into, of course, more towards, of course, we see batteries and digital storage, super capacitors, etc. And of course, is coming down to smart energy storage systems. And also we did the search, and I asked one of my senior researchers to really check the literature for me, and that was recent, to be able to identify really top 10 subjects in the field of energy storage. And you see number one, thermal energy storage, phase change materials, number two, electrochemical energy storage, and so on and so forth. And you see down to nano particles and additives to be able to really improve the storage capacity. So becoming very important. And also we looked at the search. I asked this time, include the opportunity or opportunities to be able to see the subjects. So which subjects would be really more critical. And then you see now the order changes, and we have got lithium ion batteries, and then hydrogen storage, integration to renewables, and becoming really critical that way. And also looked at the energy storage, this time with integrated energy system, because at the end you need to make it really part of energy systems. And of course, in this regard, and what we have got, of course, number one is going to be electric energy storage, integration to renewables, efficiency really becoming top three, and the rest, of course, is follow. So these are somewhat very critical. And also wanted to show some recent works completed by my group on different things. And of course, coming down to energy storage, of course, doing solid hydrogen storage and really making it by using waste. And bio waste is something very critical to consider, and different types of bio waste considered to develop these and really experimentally study and look at the hydrogen storage at different operating conditions, and to be able to really investigate how much hydrogen is potentially possible to store. And basically, potentially hydrogen, of course, storage capacities. And then also, of course, the other, of course, coffee waste. And this was also another case and studied to look at this also, of course, based on the active carbon derived. And then similarly, tea waste as well. So these are really providing good opportunities, and this was a kind of covering bio waste. And also we looked at the, this was, of course, and a feasibility study, comprehensive feasibility study, and really with an industrial partner, and as part of this study to look at the, of course, entire energy system. And similarly, the key was really hydrogen storage options, but not necessarily really storing hydrogen only in the form of hydrogen, but making it in the form of electro fuels. And this was really when you have hydrogen, and of course everybody knows that hydrogen is going to play a critical role as a fuel, as an energy carrier, and more importantly, as a key feedstock. So when you have a green hydrogen, what you do, you go one more step ahead. Of course, you synthesize into natural gas or methane, methanol, CNG, LNG, ammonia, and all these will be really possible to make. And we made it as part of these clean energy systems, and through various specific processes,
And then also, and then we had the comprehensive scenarios really to investigate each, and then really do the feasibility studies. And also we looked at the, of course, energy storage materials. And in terms of energy storage, and we had the ammonium formate, I had a couple of students of mine working on, and this was really to look at the calorific values of this. And to be able to, of course, as you can use it as a fuel, but more importantly is going to be really as a key hydrogen storage option. And that was really what we have also investigated, looked at the values, and we have found that really potentially quite promising. And then to look at also additional subjects, and we have been doing it by developing thermochemical cycles, especially started with copper chlorine, and later magnesium chlorine, and iron chlorine, and those have been really in that particular family to study. And this is really showing our copper chlorine cycle, three-step, and we developed and built and tested in the lab. And of course, we had the, of course, a pilot plant as well. So the key in here now, what we can do, especially if you are operating these thermochemical cycles, let's say you require high temperatures, and if you are making it really renewable base, you need thermal energy storage to be able to supply the heat accordingly to be able to operate the cycle. And this was one interesting case to study. And then looking at these options, this is, of course, having energy storage options. And we have a solar energy system, especially concentric PV or concentrated PV panels, and PVT systems, and having the multi-generational system, and to be able to really including thermal energy storage options, and using, as you see here, thermal energy storage system in terms of course, molten salt, and then having also compressed air storage as a part of this. And then this was interesting, having also one, this is a two-step series chemical looping cycle for hydrogen and sulfur production. This is mainly, we have a hydrogen sulfur problem in several sectors, including gas and oil, and also more importantly, even here in the Black Sea. So the key was, why not to develop an integrated system where we can incorporate energy storage into options as well. So this was the whole point, to be able to disassociate the hydrogen sulfur into hydrogen and sulfur. So that was very interesting, and incorporating storage options as well. And then another system more recently to look at this, of course, compressed air energy storage. And we do have a tri-generational system to be able to produce power, cooling, and hot water. And that was really the key. And then also worked on supercapacitors, especially we had the waste, bio waste, and to investigate and look at the options, and whether or not we can develop something more efficient. And this was something, really we had even starch, potato starch being used, and having really graphite and starch-based bioelectrodes used in supercapacitors. So tested them and developed them, and really we have industrial partner who is interested in. This has just been completed, one specific project, And this project is very unique in Ontario. We haven't yet published this, but just submitted to one journal. This is in Ontario. And the key was, why not studying the abundant mines potentially for compressed air storage? And then what we had, the government shared its database with us and listing 6,207 abandoned mines. And then really what we did, we have studied all of these, and then to be able to see which ones would be potentially suitable for energy storage and doing compressed energy storage, and really looked at the, of course, specific volume, and then also geologic formation, and also, of course, conditions. And really we did a comprehensive study, and then this way we have, of course, compared them as well. And so it was very comprehensive, and different sites identified. And this is something very critical. And over 6,200 sites, and only for the three viable sites. So this is also good number, naturally available to be able to compress air and store it accordingly. And further maps we prepared, and this was very interesting, and we have studied those. And then another study, this was very interesting, and this is my final section. And in here, underground hydrogen storage. And if you look at the storage options available, of course, we do have physical, and then also, of course, this is pressurized storage, liquefaction, and material-based storage options. But of course, when you look at the capacities, and we need something much bigger and larger. So obviously, we considered underground hydrogen storage. And of course, there are options. Salt caverns will be one of them, depleted gas reservoirs, and aquifer fields. So when you look at, these are becoming really potential options. So the key now, of course, we consider different criteria, from cost to, of course, flexible operation, reliability, and capacities, and also, of course, geological formation as well, and looked at this. And really did the search. I asked also my researchers to look at what critical subjects are coming out if we are going to really focus on underground hydrogen storage. And then this is, you see, geological systems, reservoir engineering, and this, of course, becoming specific processes related, geomechanics, monitoring and digitalization, risk and safety, and sustainability, really becoming very critical to consider. So the problem is not one-dimensional, it is multidimensional. And also, of course, also considered this, as mentioned, and looked at this. We looked at different, of course, options, and also what is critical. In storage, you may do short term or long term. When you do short term, might be daily and weekly, and but long term, of course, is going to be, let's say, seasonal or annual. And that's why these are becoming very critical. And also, of course, studied different geological formations and different, of course, locations and options, and see these discharge durations, and to be able to see
which ones would be feasible. So that was a whole point. And in this, really, there were specific problems coming out, and really to tackle with, especially to be able to achieve a sustainable future. And of course, these are, you see, from energy security to grid flexibility, stability, and flexible hydrogen supply, etc. When you look at this, and of course, coming up to seasonal and long-term storage becoming very critical. And also looked at the challenges, and of course, really becoming some risks as well. But the risk part, of course, had another comprehensive section. I separated that, but listed challenges here as being studied by my group. Geological challenges, hydrodynamic challenges, geochemical challenges, biochemical challenges, engineering challenges, environmental challenges. So when you look at here, underground storage is not going to be really an easy storage option, especially for hydrogen. You need to really tackle with all these challenges. And also we did this, and we of course considered 24 criteria. And all these criteria, but brought them down. These are in terms of five categories you see here, and looked at the, of course, in terms of sustainability scale, and what would be the scores. And you see here, depleted gas reservoirs would be really the most suitable and sustainable options for large-scale hydrogen storage. And then the rest follows, as you see here. And then we have, of course, as you see here, and rock caverns, and these are, as you see, in different, of course, scores. And in terms of roadmaps, and this is something very important, and which will be, of course, historically to be able to see. Now we see a pilot demonstration and scale-up works really being undertaken, but eventually we need the underground hydrogen storage really widely deployed around the world. And then finally, closing by saying that really, if you look at the decarbonization by concept, we have issues there, and it is really, we need to make it very clear. This is not about decarbonization. This is technically about the consumption. We need to really minimize consumption. That's the problem. Excessive consumption is really the source of this problem. We need to change our energy diet, focus on clean energy technologies, and really incorporate energy storage into, and compressed air energy storage and underground hydrogen storage would be really critical for large scale applications. And ultimately, what we try to achieve really is sustainable development. So it has been 33 minutes. So thank you.
Thank you very much for your presentation. What I'm curious about, we are highly dependent on, in Turkey, coal in our thermal plants. For example, in Soma region and Soma lignite, which heating value of which is approximately 7,000 kilocalorie per kilogram. So this dependency actually uh, effect of this dependency is really make our all processes in industry, in climate change, is emissions. Maybe in 30 years more, we have coal reserves in Turkey. So, what's your opinion about this?
You know,
Coal or renewable, not easy, and rehabilitation of thermal plants, maybe like in China, with natural gas instead of coal, maybe an alternative. But what's your opinion?
as far as I know, only about 40% of the thermal power plants in Turkey using coal. And the coal, and we have our local, we have, of course, high grade, and at the same time, low grade lignites, you know. But we are also importing coal from Russia or other neighboring country. So the key, of course, if we are going to talk about really how to reduce carbon emissions, and of course, Turkey has made the commitment to be a carbon neutral country by 2053. So now, in terms of, and sign the agreements, by the way, internationally, so really bound by. So, and that's why, in terms of renewable electricity, and there is a big jump in Turkey. You know, that's why such increase is going to continue, and really focusing on renewables. But the key right now, and this has been the investments have been more than what was expected, and that's why storage is becoming very critical, and that's why many, let's say, companies, especially these renewable energy producing companies in terms of solar and wind, they are suffering, they are being penalized at certain specific hours that they produce more, the grid doesn't need. So that's why there is incentive provided for storage options, but probably this is going to be very soon expanded to cover hydrogen production, and which will help develop a hydrogen economy as well. And this is also another plan for the ministry as well. So technically, being part of this, and Turkey, of course, will continue. And I believe eventually, probably by 2035, and there will be no more coal powered thermal power plants. And this is what I expect. And accordingly, the ministry is really trying to do it that way. And that's why what is going to replace this? Renewables and nuclear. So Akkuyu is now operational, and that's why eventually all these reactors and additionally small modular reactors are planned to really deploy. And obviously, this is going to be fully depending on renewable electricity and nuclear electricity. And Professor Johara, I think, raised his. Anyway, so I use a shorter time for my talk and giving you guys more time for questions.
Oh, you're so generous as always, Ibrahim. Thank you very much indeed. A couple of questions, actually. One about something you are very passionate about, which is hydrogen.
Yeah.
In the previous talk, we did mention the word cooling down. It is actually cooling down in Europe, the focus on hydrogen. And that is mainly, as you know, mainly because of the green hydrogen cost. It is still high and it's not sustainable, it can't compete with others. So if you can just give us
Okay.
an idea about where things are
You know,
going.
this is something very sensitive subject and really affected by the political moves. And the politicians are affecting the decisions greatly. And we have seen this in the US. Why? The guy came to power, and then what happened? Canceled all clean energy projects, hydrogen projects, cut their fundings, and so on and so forth. Even removed renewable energy titles from all government institutions. And many people know, of course, NREL,
National Renewable Energy Laboratory has been, of course, in the literature, of course, operational for many decades, very well known. What happened? They changed the name, became National Lab for Rockies. So this is the point now. And then what happens? Many countries watch USA and then move accordingly, because earlier, really the clean energy program was really widely and affected several countries, not necessarily, of course, every country, but really slowed down the move. And the other challenge behind the hydrogen economy and the requirement, the infrastructural requirements are really huge. And that's why, this is required. Electricity, especially why we go for electrification, easier. You produce electricity, and then that's why, widespread electric vehicles all around. And what you do, you get a charger, of course, and you do the charging. Or let's say charging stations available everywhere without requiring infrastructural changes. But the key question, is it really sustainable? Is not really sustainable. If you look at the emissions, I always give the example. And when you have a gasoline vehicle, you are going to emit more than 150 grams of CO2 per kilometer driven. But when you have an electric vehicle, this is going to be between 25 to 40 grams of CO2 per kilometer driven. But when you have green hydrogen based fuel cell electric vehicle, and this is going to be 2 to 4 grams of CO2. Why? Because when you study the life cycle and you have a vehicle cycle, you have fuel cycle. And when you come down to battery electric vehicle, you have battery cycle. And the battery cycle is bringing those embodied emissions and making it really worse for electric vehicles. So that's why, if you look at it, is this really sustainable to really develop the society fully electrified? I don't think so. And that's why, and we need to really think about the following. Also, the mentality in hydrogen economy, many people think, oh, we need to make everything on hydrogen. No, what you do, and you produce hydrogen and turn it into other alternative fuels and chemicals. That's why I say oil refineries eventually will turn into hydrogen refineries. So what we do, we will have hydrogen refineries where we can synthesize really all these alternative fuels and chemicals and continue using them. The key is not going to, those fuels and chemicals are not going to come out of fossil fuels, are going to come out of hydrogen, green hydrogen. So this is the way, and we need to develop really a widespread this. I see one more.
Thank you for your excellent presentation. As you know, we need to consume. This is the reality. But at the same time, we need to decarbonize. How can we make a good balance between
Okay.
two? That is the question.
So that's why I made it clear that, the problem is not about decarbonization. The problem is about consumption, and that's why the consumption we need to reduce consumption. We need to minimize it. But at the same time, we have been using carbon or carbon sources, and now mainly relying on what? Fossil fuels. We need to change that. We need to change it into biocarbonization. So from fossil fuels or fossil carbonization into biocarbonization. So this is going to be the way. So we will always need carbon sources. So that's why biocarbonization is going to be critical. So I call it recarbonization rather than decarbonization. We need to recarbonize and make it really on carbonization. But in total, still 44 minutes.
Thank you very much, Professor Dincher. Now, I would like to present a plaque of appreciation to Professor Ibrahim for his outstanding contribution to West 2026. So, may I kindly invite also Dr. Professor Seda Keskin Avcı. So, she's the chair of the keynote session. And could you please present? Tamam hocam. Tamam. So this concludes our morning session, and we would also like to invite everyone, all the presenters, the keynote speakers, and our participants, in order to be able to take our official WESC 2026 group photo. So may I kindly have you on stage for the group photograph? Thank you.
Sizler de gelin, herkes, gençler.
Merhaba hocam, nasılsınız? Her zamanki gibi aynı. Aynı takım.
I think you might need to go there to be seen. Oh, I like that. It's a good thing.
Hello again, everyone. So now we will have our lunch break from 1 until 2. So, and it will be on the 9th floor. And we will be continue our sessions at 2 o'clock. So enjoy your lunch. Tamam.